Hi, let's talk about Mohr Circle. In this case, what I would like to achieve at the end of this lesson or at the end of the series of videos is to find the representation for a three-dimensional stress state or state of stress case. As you're seeing in the figure right now here, this is kind of the final representation we're going to get in our Mohr Circle. And we know, or if we can start by saying that you by now know what a Mohr circle is because you have taken it in the previous lessons. However, if you're watching this video and you don't know what a Mohr circle is, we use Mohr circles kind of to represent the transformations between one orientation on a stress tensor of the Cauchy stress tensor to another orientation, meaning that using the Mohr circle, it would give us the full information about what are the maximum stresses, normal stresses, shear stresses, as we are rotating this infinitesimal cube as we were seeing in the past. So that's a Mohr circle. It's a two-dimensional representation of the transformation of the Cauchy stress tensor. So that's kind of the way, that's kind of the main use of this Mohr circle, and it's still useful even though it's been a while. It's been around for a while. It's still useful, and it gives us at a glance what are these maximum stresses and in which planes are those maximum stresses located. Before going into the full three-dimensional concept of what is or what's the concept for a three-dimensional Mohr circle case, I want to start with the two-dimensional case. In this sense, let's say I would like to start with a review of what was done. You might know this, and if you feel that you are let's say okay with what I'm going to do now, then you can jump to the next video that will I present a more in-depth information about the three-dimensional case for the Mohr circle. So, but let's start with the two-dimensional case, and let's try deriving the principal stresses for a two-dimensional case. We already did it for the three-dimensional case, but this is going to allow us to build the circle itself. All right. So I have here the initial was what we want to get, and I will start this two-dimensional case not with an infinitesimal cube, but with an infinitesimal plane. Let's put it in that way. That plane is going to be something like this. I'm going to have a plane, and this plane I'm going to have a Cartesian coordinate system XY, and I will have my stresses on the faces of this plane here. Of this, I will have stresses in the y direction. These are normal stresses. And also I will have the shear stresses corresponding to each one of these sides here. We are going to keep writing down or drawing down these stresses in the positive direction, as we have established before. So we have here, this is this tau xy. Please remember the convention, the sign convention. We're going to have here tau yx, in here tau xy, and in here tau, sorry, this one is tau yx also, and this is tau xy. Perfect. The reason you are going to see, or you see first, just in a plain representation of the state, the stress of state, the state of stress, get confused with the wording, is that many applications in structural mechanics or mechanics of materials could be simplified by just using the planar case of the state of stress. And the idea behind this is that you will have two stresses that are dependent on each other, but you will have a third stress that is independent of the previous two. Meaning that for this case, We are not writing down or drawing down the z direction of this Cartesian coordinate system. It means that it is not that it doesn't exist. It exists, but the values of that normal stress pointing in the direction of the z-axis, it exists, but it is independent of these stresses represented here, these sigma x and sigma y. And that's important to recognize that, having this just one stress and knowing just that principal stress in that direction, then we could utilize this plane representation to find out the other two principal stresses. This is pretty important. That's why it's a very nice simplification of the infinitesimal cube. Let's say, what do I need to do with this? So this is pretty straightforward. We have seen this, but this is not completely interesting. What it is interesting is to know what's happening when I rotate this cube, or sorry, this plane, this square, in kind of in a position in another direction or orientation. Kind of is similarly to say that, okay, what about if I cut this plane with this line? This is going to give us kind of a cut plane here. And I say, okay, I want to know what are the stresses in that inclined plane. Something that we did for the three-dimensional case. I'm going to extract the wedge created by this new line or dashed line that I wrote there. It's going to be something like this. I'm going to put it here. I will have this face, and then this line here. And this is going to be, again, I'm going to write it down. So this is going to represent, if I call this point E and this point F, this is going to represent my point F and this my point E. So I took the plane, I cut it at an arbitrary angle, and that's going to produce me this wedge or triangle here. Good. I will write down the remaining or the stresses acting on this wedge. Definitely, I will have acting these normal stresses in these faces. Also, I will have acting the corresponding shear stresses in here. XY. But as I cut the plane or this square, I'm going to have a new normal and shear stresses corresponding to the area formed out in this wedge. Meaning that if I see this wedge from a perspective point of view, it's going to be something like this. It's going to be the triangle here, but I will have this wedge here. Great. Then from this cut, two stresses are going to result. The first one is going to be a normal stress, of course, normal to the new surface represented by the line EF. I will call it sigma NN. And a shear stress tangential to that face there. I will call it tau NS. Sigma NN because it's pointing in the normal direction, and tau NS because it's pointing in the is applied in the normal phase, or let's call it in that way, but pointing in the shear direction or tangential direction. Perfect. Now, as you know, we need to make use of the equilibrium equations to find out what the relationship between them, or the relations between these different magnitudes represented in this new inclined plane. If I'm going to do then equilibrium equations, it means that I'm going to use forces. But here I have represented just stresses. So to turn these stresses into forces, I need to multiply them by the areas where they are applied. Let's make a study of the areas. So first, we have this wedge here And I know that, for example, sigma y and tau yx is applied in this area here. I know that, just another color, that sigma x and tau xy is applied in this area here. Now, what's the value of those areas? I could say that these, even though these have certain depth here, we'll call it dz. You could say that the area represented, the new area created by the points EF, that line, this area. I could say for these purposes that this area is going to be equal to 1. As this is oriented at an angle theta from kind of the inclination is oriented at an angle theta, I could say then that this angle here, or this area, is going to be what? The original area, the big area represented by the section created by the line cut plane EF, times the cosine, times the sine of theta. And I could say that this area is also represented, or is represented by the area times the cosine of theta. Now, as I impose, for a practical matter that area is equal to 1, then this is going to end up being that, this area is going to be equal to the sine of theta, and this area is going to be equal to the cosine of theta. Good. You're going to see why this simplification is going to turn out really good for us. Now, okay, I would like to write down again how this looks like from a Cartesian coordinate point of view. That is, I will write down my Cartesian coordinate system here. And I will represent all my stresses in this Cartesian coordinate system. I know that this is X, this is Y. Then I know also that I will have another coordinate system created by the cut plane. And I will have this line, and then I will have a perpendicular to this one. This is going to be my X prime and this Y prime. Then let's understand that X prime is aligned with the NN axis. Then I'm going to represent or draw on top of these Cartesian coordinates the corresponding stresses. That is, first, let's draw, the one that we are interested in. So we have this sigma NN. We have a shear stress here, tau NS. I have the normal stress sigma X, the normal stress sigma Y, but I also have the shear stresses. I would represent it like this. Please follow this, and I'm trying to mix up this. I will write it on the same length, kind of arrow length, but it doesn't mean that they are the same. It's just for a representation point of view. And then here I will have, which one is it? Yeah, this one here. It's pointing up, tau XY. Yes. And if I want to remember the angles, how it goes, I know that this is represented something like this. It should be something that this is theta. This is theta also. It repeats in here. And if I follow the angle here, it repeats in here. Good. I believe we're ready to apply the equilibrium conditions in this system here. But which would be the directions to follow to apply the equilibrium conditions? Because I could say, okay, I want to know equilibrium conditions along the x-axis, or equilibrium conditions along the y-axis. That's doable. We could follow that way. However, to simplify things, I am doing these equilibrium conditions because I want to find out what are the values of the normal stress in that inclined plane and that corresponding shear stress. Then for me, I believe at this point, it would be more convenient to use the directions of x prime and y prime to do this equilibrium formulation, if we can call it like that. Let's start. To put it in this form here, yes. If I say, okay, I want to know what's happening in this x prime direction. Good. It's going to be, okay, let's have this. So the x prime direction is this one here, pointing in this, aligned with the normal stress of the inclined plane. If I perform the force sum in this direction, I will have what? I will have that sigma nn, that's the first one, minus, I would have, let's start with the normal stresses, sigma xx. Let me recap on this, because it was, we already defined that the areas of these, where these stresses are applied, are can be represented if we make the distinction or the simplification that the area of the inclined plane is equal to 1. Just as it works because in the end, if you notice with the three-dimensional case, many of the areas canceled out, and this is going to be the same here. So in this case, I'm going to have that the vertical phase is going to, the area of the vertical phase is going to be cosine of theta. The area of the horizontal phase is going to be sine of theta, and meaning that the force applied to the force caused by the normal stress on the inclined plane is going to be the stress, normal stress sigma n times the area, but as the area is 1, then I'm going to have just sigma n. That's what I wanted to explain. Then I'm going to work with the normal stresses. Sigma x. Sigma x is being applied on the vertical phase, and that's going to be, as this is negative, it's going to have minus tau x times the area where it is applied, cosine of theta. Then, but I need to orient or transform this vector that is applied on the x-axis to the x prime axis. And to do that, I have to multiply it by cosine of theta again. I need to write it in here, in this axis here. Then sigma y, also negative, is going to be applied on the horizontal phase, which has an area of sine of theta, and is going to be aligned with this axis x prime here, that would be a transformation of sine of theta. This is sine of this part here. Then what is remaining is the, let's see, the stress tensor, which I have. The first one is going to be applied in, okay, this is a mistake here. Sorry about that. This is, he needs to be positive, and to be positive, it has to be aligned in the negative direction because it's applied in the negative phase. XY, sorry about that. Please change this. I hope that I could see it beforehand, but it's going down. Yeah, minus, let's start with this one here, shear stress YX. YX is applied on the horizontal face, this one here. And that means that it's going to have to be multiplied by the area sine. Let me change this. Tau xy, sorry, again, yx. Tau yx applied on the horizontal face sine theta. And then to transform yx to the x prime axis, I need to multiply it by the cosine of theta. Minus tau xy that is applied on the vertical face, which means that I have to multiply this times cosine of theta to convert it into a force. But then to transform it to, or to take it to the x prime axis, rotated to the x prime axis, I need to multiply times the sine of theta. I'm going to group terms here to see how it looks like. And this is equal to 0. Then I will have sigma n. Actually, I'm going to write that right now. Sigma n equals to sigma x cosine square of theta minus sigma y sine square of theta minus here. Remember what we talked about, the reciprocity of shear stresses. This applies here also. So meaning that these two terms are equivalent or equal. Then I can write this 2 times this term. It would be 2 times tau xy sine of theta cosine of theta. Let's call this equation 1. Good. Now let's formulate the equilibrium for the other direction, y prime. That is what happens in sigma fy prime should be equal to 0. Refresh this here. Then in the y prime direction, let's start with the same. I would have tau and s, yes, plus sigma x, which is applied on an area of value cosine of theta. But to rotate it to the y prime axis, I need to multiply by the sine of theta. Then minus sigma y, which is applied on a face with area sine of theta. And to convert it or to rotate it to the y prime axis, I need to multiply it by the cosine of theta. Good. Then the shear stresses. I would have the first one would be plus, yes, plus this tau yx, which is applied on a face with area sine of theta. But then to move it to, or to rotate it to the y prime axis, this one here, I need to multiply it by the sine of theta. The same in the other case, tau, yes, xy, need to subtract this tau xy, which is applied on that face with area cosine of theta. And to locate it or to rotate it in the y prime axis, I need to multiply that times cosine of theta, and this is equal to 0. Yeah. Then if I group terms and put things in the right side of the equation, I would end up with this. Tau ns equals to, let me see. Let's group it right away. It would be tau xy because of the reciprocity of shear stresses. Yes. Sine, or let's put it, yeah. This negative goes to the other side positive. It would be cosine square of theta minus sine squared of theta. Yes. Then plus sigma yy, seeing this, minus sigma xx times sine of theta cosine theta. And let's call this equation number 2. Good. Now we found, let's recap to see what we have done. Let me change this one here. This has to be going, this has to go down here. Tau xy. Then we want to achieve, or we want to get to the point where we can use the results of the principal stresses in 3D and represent them on a 2-dimensional graph called Mohr Circle. And this Mohr Circle would allow me to find out the other stresses in, if I rotate that cube differently, or I rotate it or orient it on another Cartesian coordinate system differently, then this representation could give me what are the maximum stresses that I could find. And then it's a pretty graphical tool and pretty beneficial tool in the sense that I can, in one glance see what are the maximum stresses without trying to iterate with the formulas to see what are the maximums or minimums of them, of stresses in a point of a body. Then I started to build this 3-dimensional case of the Mohr Circle. Then I started with the planar case, and the important or the interesting case in the planar case is to find out what happens when I try to find out the normal shear stress on an inclined plane. And that's what we have done here. So we cut the plane, we draw our normal and shear stresses, then we represented them on a different Cartesian coordinate system to look at it better. Finally, we postulated the equilibrium equations to get to know what are the values of these normal stress and shear stress coming or acting on this inclined plane. So I will stop the video right now in the sense that kind of to create smaller chunks of information, because I understand that 15-minute long video or 1 hour long video is not convenient. So I will cut it here, and then in the next step, what I will talk is about what are let's aim to find in the next video what are the principal stresses in this planar case. Thanks a lot.